plenary session of Strings 2018. I guess that if I am the chair of that last session, it's not an accident. This gives me the opportunity to make an announcement about Strings 2019. So thank you, Hiroshi, for having given me this opportunity, which I will seize. So Strings 2019 will indeed happen in Brussels. Oops, like this. Oops. In Brussels in July of 2019, and I would like to say a few words about the organizing teams, about the venue, and about the dates. So, but first, maybe where is Brussels? Well, Brussels is in Belgium, and where is Belgium? It's a very small country in the middle of Europe, in the middle of that part of Europe. And it's indeed a small country. You have here the scale. So I think in 2 hours you can cross the country. And Brussels is the capital. Now, these are some views from Brussels, the emblematic views of Brussels. I mean, if you go to Brussels, you either take a picture, or that, or the three of them. So this is the Atomium, the Grand Place, so Square Market, and Mannequin Place. Now, what are the organizing teams? So these are theory groups from 6 Belgian universities. So the Université Libre de Bruxelles, the Vrije Universiteit Brussels, Katholieke Universiteit Leuven, Université Catholique de Louvain, Université de Mons, Universiteit Gent. And this consortium is headed by the International Solvay Institute, which will be in charge of the logistics. Now, for those of you who know Belgium, you have to admire how politically correct this consortium is. In particular, there are 3 French-speaking universities and 3 Dutch-speaking universities. But there are also many other balances that have been respected. I won't go into here. Okay. Now about the venue. The venue is interesting. It's a former home to the National Radio and Television. It's called Flagey. Well, it's maybe not so interesting from the inside. It looks a bit like a big boat, but it's interesting nevertheless. It was built in the 1930s, and there are many at the time of the Art Deco, and you can see that more in the inside. We will have the whole building for us for the Strings 2019 week. And the lectures will be given in the so-called Studio 4, which is where the radio orchestra used to play and to make recordings. So the acoustics is excellent. There are also some extra things that we might use. But so you can see that indeed these are things that are visible in the venue. Now the dates, it will be the second week of July. Well, that is actually first week where all the people involved in the organization will be free from university duties, etc. But you must ask the question, why start on a Tuesday? Usually it's from Monday to Friday, and we have here Tuesday. Well, the reason is the Tour de France. Indeed, so what is the Tour de France? Maybe not all of you know what is it. So the Tour de France is a biking race that takes place every year. So it's a multi-stage race going around France, but also sometimes passing through nearby countries, and lasts about 3 weeks. Now, in 2019, they will start from Brussels. Why will they do that? Well, it turns out that 1 year after the discovery of the Veneziano formula, Eddy Merckx won his first Tour de France. So Eddy Merckx, again, for the people who are not familiar with biking, I will say a few words about Eddy Merckx. Eddy Merckx was a Belgian biker. He won 5 Tour de France. He won many other competitions. In the mind of the Belgians, he was the best biker ever. He was called the cannibal because he won everything. And so he won his first Tour de France in 1969. And bikers also make celebration, and they will celebrate his the 50th anniversary, his first victory, by organizing 2 stages in Belgium, like Brussels, see, on the 6th and the 7th of July. To be more precise, the Saturday they will leave from Brussels, go in the countryside, back to Brussels, but on Sunday they will have a stage entirely in Brussels. And the venue, our conference, is here. So we thought that we should avoid competition with them because we don't want to cast shadows. And also, we are supporters of Eddy Merckx after all. And also, I think we should leave them some hotels free. So I think the hotels will be completely full Friday, Saturday, Sunday. So that's why we start Tuesday. So I've told you about the date, about the next conference. Is all invited us if you like by earlier. But we are still in 2018. Conference, and I would like to start it by congratulating Hiroshi and the Okinawa team, a wonderful conference that has been put together. It has been remarkable, not only from the scientific point of view, but also from the organizational logistic point of view. So you have put the standard very high. It's something that we will try to match, but I'm not sure we will be able to, but we'll do our best. So really it was, and there are still 2 more sessions to come. So the cherries on the cake still to come, but it has been a wonderful conference. And so not only do I want to congratulate the organization and for the conference, I would also like to thank you. And I think I'm speaking here in the name of all the participants for the hospitality and this. Now, since I'm afraid that after the end of the session, people will rush for coffee, and after the other session, they might rush for buses, suggest that we give a loud applause already now to the Okinawa. Is this part? So our first speaker is Masanori Hanada, and he will talk about black holes and random matrices 2, new universality at early times.
Thank you very much. Can you hear me? Okay. So first, thank you for having me here to give a talk. And I think the meaning of 2 in the title will become clear soon. And this talk is based on collaborations with these people. And the front is very smart student, Stanford. Brian is in Maryland. Hidehiko should be somewhere in this room, and apparently he is recently very happy. And Masaki is in Kyoto University. And actually, he's my high school classmate. And we came here for school excursion. And it was such a life-changing event for him, if I remember correctly, because he couldn't ride on bike before coming here. And after going home, he could. So anyways, if my memory is correct, I think he will text me immediately. And so I want to talk about the chaos. The classical chaos is typically characterized by sensitivity to a small perturbation, or equivalently positive Lyapunov exponent. In principle, we can solve equation motion precisely, and we can determine a trajectory in phase space precisely. And if we add perturbation at time t equal to 0, it can grow exponentially. And this lambda in exponential is so-called Lyapunov exponent. And if lambda is positive, system is sensitive to small perturbation, so it's chaotic. And for quantum chaos, these days people use sensitivity to small perturbation as well, like in classical chaos, by using so-called out-of-time order correlation function. Historically, more popular way of characterizing quantum chaos is universality in energy spectrum. Namely, if we calculate energy spectrum from Hamiltonian and look at fine-grained structure, if system is chaotic, it's indistinguishable from a random matrix. And here I plotted the nearest neighbor level spacing calculated from SYK model and random matrix, and they totally agree. And if we look at such universality, so it's a fine-grained energy structure. So if you look at the correlation function, you can see such universality at a very late time. On the other hand, the sensitivity to small perturbation is typically early time physics. Last year, Steve Schenker gave a talk titled Black Hole Under Random Matrices about this universality. And in this conference, Douglas's talk was related to this. And today, I want to suggest that random matrix is hidden here as well. And not just quantum theory. Also in classical theory, we can see random matrix. And it seems that there is an interesting connection to quantum gravity. And the key concept here is Lyapunov exponents, not just the largest exponent, but a spectrum of a lot of Lyapunov exponents. In classical theory, phase space is multidimensional, so we can add perturbation to various directions. And to some direction, it can grow. To some direction, it can shrink. In order to characterize the sensitivity to perturbation at time t equal to 0, by using z to denote coordinate x and momentum p simultaneously, we can define such matrix mij of t. Okay, so derivative of zi of t with respect to zj of 0. And apparently, this characterizes the response of the system to perturbation at time t equal to 0. And we can calculate the singular value of this matrix Si, or equivalently, we can define L, which is m daga m, and we can call the eigenvalue of this to be Si squared. And finite time Lyapunov exponent can be defined by 1 over t times log of Si. This Si grows exponentially if system is chaotic. In order to see the importance of the Lyapunov exponent, I want to use this example. So suppose there was two systems consisting of 1,000 degrees of freedom. And in one case, lambda 1 is 100, but all others are 0. And in the other case, all lambdas are just 1, which is more chaotic. Okay, so if you look at just the largest exponent, this looks much more chaotic. And in order to answer to this question, we should look at we should define so-called Kolmogorov-Sinai entropy, which characterizes entropy production rate. Suppose our knowledge about the initial condition is not precise, and we only know that the initial condition is somewhere in this disk. After some time, this blue region can be stretched to some direction and can shrink to some direction. And it's described by Lyapunov exponent in this way. In order to define coarse-grained entropy, we introduce mesh and count the number of cells which is needed to cover these blue regions. At first, we only needed only one cell, but at some point, we need more cells to cover this stretched region. And the number of cells which is needed to cover this region is apparently proportional to product of exponential lambda. with positive lambda. And the coarse-grained entropy is basically log of this quantity, and which is sum of positive lambda times t. So in this sense, Kolmogorov sign entropy, which in this case is defined by sum of positive diaphragm exponent, can describe entropy production rate. Then in this case entropy is 100 versus 1000. So in this sense, this latter example is more chaotic. And actually, the same situation appears in the case of physics of black hole. So Hawking found that bigger black hole is colder. That would mean typically diaphragm exponent is smaller. Does it mean bigger black hole is less chaotic or not? In order to answer to such question, we need a microscopic description of black hole. So let's use a D0 brane matrix model for simplicity. This is a theory of n by n matrices. And the diagonal entries describe location of D0 branes, and the off-diagonal element describe open string excitation connecting between D branes. And if all eigenvalues are sitting closer and off-diagonal entries are excited, we would have D0 branes connected by string, and it looks like a black hole. And we can also imagine block diagonal configuration. Here off-diagonal entries are 0. That would mean 2 black holes. Or we can also imagine gas of D branes without any string excitation. Then if we imagine the merger of 2 black holes, okay, so we at early time we have 2 matrices, 2 blocks with 0 off-diagonal entries, and after merger, off-diagonal entries are fully excited. And let's denote the temperature of larger black hole and smaller black hole by T large and T small. And for simplicity, let's consider high temperature region of this matrix model, which can be described by classical treatment. And then it corresponds to highly stringy black hole, but still it's fine. The essence of the physics doesn't change. Okay? And then we can easily show that the energy of this black hole is up to some constant factor, which is actually 6. It's n squared times temperature. So energy is n squared times T large. But at early time, block was smaller. So each black hole would have energy n over 2 squared times T small. And we have 2 blocks. Then, so larger black hole has a temperature which is 1/2 smaller than original smaller black hole. This is how black hole becomes colder. And we can also show that in this high temperature region, each diaphragm exponent scales like T to the 1/4. So diaphragm exponent becomes smaller after the merger. But point here is at early time, these off-diagonal entries correspond to very long open string connecting different black holes. And they are so heavy they cannot be excited anyways. So they are not chaotic mode. So diaphragm exponent corresponding to such modes are 0. Okay. And each exponent scales like this. So if we calculate Kolmogorov sign entropy, roughly speaking, this system has n squared times T large to the 1/4 as entropy. But here we have only 2 times n over 2 squared times T small to the 1/4. And if we just substitute this relation here, we can show that the Kolmogorov sign entropy actually increases. In this sense, larger black hole is more chaotic. And if we just look at the largest exponent, we cannot see such physics. So I'm not sure if this was good enough motivation for you to look at the spectrum, but I hope you have some motivation to look at the spectrum now. And based on such motivations, we studied the spectrum of diaphragm exponents, and we found interesting universality, which I will introduce from now. First, let's start with classical theory. So this is important relation, which actually I have already shown. So we use Z to denote coordinate X and momentum P simultaneously. Okay? And this Mij of T characterizes the response of the system to perturbation. And this L, which is M daga M, which is easier to handle because this matrix is a Hermitian. And anyways, from this we can define a singular value Si or Si squared. And by using this Si, we can define the diaphragm exponent. And in general, this is a function of time. And at sufficiently late time, they become constant. And this quantity at classical level, by using a chain rule, we can just decompose it the product of similar quantity for infinitesimal time evolution. And then by truncating at certain order of delta t, we can calculate such metrics with good precision numerically. So it's tedious but straightforward to calculate spectrum. And we apply it to the zero-brain matrix model. This is Lagrangian, or the zero-brain matrix model is Lagrangian is the same as so-called DeWitt-Hoppe-Nicolai or Banks-Fisher-Shenker-Susskind matrix model. And we take a high temperature meter where classical treatment is okay. So fermionic term is negligible there. And we can just discretize the equation of motion, classical equation of motion, and solve it numerically. And gravity dual is black hole in type 2A string. And in high temperature region, actually it corresponds to highly stringy black hole, which means the black hole and the strings are more or less the same size. So alpha Poynting collection is big, but still, should be well-defined gravitational theory. So this model is classical, but very special classical theory. And with Guy-Gurari and Steve Shenker, I calculated the Lyapunov spectrum for single black hole, right? And then we could see that so this direction is lambda, this direction is density of lambda. And in this plot, we took n to be 6, and the temperature is 1, time t is 20.7. And you would ask me why it's not 20, but there's no deep reason. Anyway, and we chose a lot of typical black hole state. We'll summarize the state, and we took the average with respect to initial conditions. And then we noticed that this distribution could be fit by using these ansatz. Okay? Lambda max is more or less the largest Lyapunov exponent, and there is exponent gamma here, and this gamma turned out to be 0.5, almost with very good precision. So this is so-called semicircle distribution if we look at the edge structure. And from random matrix theory, this semicircle distribution appears very often. So we thought maybe there's some random matrix hidden behind it. But at the time, we didn't carefully study it further. And later, I decided to study the connection to random matrix more seriously. And so by using the data we took for this project, okay, so we ordered the Lyapunov exponent to this order. Sorry, this n is actually not this n. Sorry, for SU n theory, number of Lyapunov exponents is something like n squared. But anyway, then using this lambda, we defined the nearest neighbor level separation and compared it with random matrix theory. And in classical chaos communities, some people looked at the Lyapunov spectrum previously, but in classical chaos community, typically people take t equals to infinity before sending n equals to infinity. Probably this is because people think 3-body is good enough to have chaos, and they don't want to go to many body. But if we are interested in many body physics, this is actually more natural limit. And actually, these limits do not commute. And in this limit, what we found is this. So this is a plot of this nearest neighbor separation from the zero-brain matrix model with different values of n for t equals to 0 and t equals to 10. It turned out at any time, it agreed with the so-called GOE random matrix distribution. And if we deform the potential so that there is no good gravitational dual anymore, for example, by adding such mass term, it turned out this universality is gone here. Maybe it's a bit hard to see the difference, but this is plot for m equal to 3. If we add the bigger mass, we can see deviation more clearly. But we can clearly see that there is a quantitative deviation from random matrix. However, if we wait for a while, actually, random matrix sets in anyways. So at t equals to 0, we don't see random matrix. But after some time, the Lyapunov spectrum converges to random matrix. And we studied it further. And firstly, I have only shown that nearest neighbor level separation agree with random matrix. But by using so-called spectrum form factor, we could show that universality holds beyond the nearest neighbor level. And the algebraic matrix model is very special in the sense that random matrix appear already at t equals to 0. But in various examples we studied, we could see that although random matrix is not there at time t equals to 0, after some time, the Lyapunov spectrum gradually converges to random matrix. And I think this is a very generic property of classical chaos, and somehow quantum gravity is special. In this, it's kind of strongly universal in this sense. Then we try to generalize it to quantum chaos. And first of all, I have to admit that there's no consensus for definition of quantum Lyapunov exponent. But anyways, we tried the natural option. Anyways, so this was the definition of a classical Lyapunov exponent. We define this matrix M and L, which is m daga m, and then from eigenvalue of this L, we could determine Lyapunov exponents. And of course, natural counterpart of this matrix M in quantum mechanics is a commutator of z hat and its conjugate pi hat. Okay, so if z is x, this is p. If z is p, this is x. And we define the counterpart of this L in this way. So we just sandwiched operator version of this M with certain states phi. And it depends on, there is ambiguity of choice of phi. And in the following, we take phi to be energy eigenstate. And intuitively, this M hat acting on phi can grow exponentially. It's a bit technical part, but if you just sandwich this M hat with phi, then actually, though it is growing, overlap with original state phi can decrease. So actually, we cannot really see Lyapunov growth in a strongly coupled region. But by using this, we can see reasonable exponential growth. And when a system admits a classical limit, this looks like a natural generalization of classical Lyapunov exponents. So we applied it to SYK model. And instead of a counterpart of this operator in SYK model is apparently anti-commutator of psi hat I t and psi hat j 0. Okay? And this is a Hamiltonian by SYK model. And we also added the quadratic term. And if we just have this term, the system is integrable. And if we take k to be larger compared to j, system becomes less and less chaotic. Okay? And usually, when people use usual OTOC, people will take this combination. They take a square of anti-commutator and take some with respect to I and j, I think. If you do that and call a Lyapunov exponent calculated that way to be lambda OTOC, actually this is a kind of average of different Lyapunov exponent in this sense. But at a later time, largest exponent dominates anyways. So largest exponent at late time agree with the usual definition. But at the early time, with this definition, actually, contamination from a smaller exponent appears. And even at earlier time, numerically, our method seems to be better. And this is a plot for Lyapunov growth. So lambda n is the largest exponent. Okay? And the lambda times t is log of s. And this s should grow exponentially. So this is a log plot of exponential growth. And we can see straight line behavior for different values of k. And with larger k, system is less chaotic, so growth is slower. And here I plotted the k equal to 0.01. It's almost purely SYK. And we change the n from 6 to 20. And at the late time saturation, growth saturate. And these two lines show 20% and 80% saturation of this lambda compared to late time value. And we can see really nice straight line. And if we divide the y-axis by t, we can see almost a constant behavior here. So we can actually see almost a constant Lyapunov spectrum, which characterizes purely exponential growth. And this is a nearest neighbor distribution of nearest neighbor level separation. So from early time to late time, always it agrees very well with so-called GUE ensemble. There is small deviation, but I think this is finite in effect. And we studied various different values of n, but it seems that at larger n, it's going closer to GUE. And our numerical observation is that, first of all, so when k is positive, high energy modes are chaotic and low energy modes are non-chaotic. And so by changing k, we arrived at this guess. Chaotic states gives random matrix distribution, and the non-chaotic states probably give Poisson. And we also used the so-called Brownian circuit version of the model, and result data from a Brownian circuit version is consistent with this guess. And we also studied the spin chain, okay? And this is so-called XXZ spin chain. And this is so XXZ. So this is just a one-dimensional chain of Pauli matrices with a random magnetic field along z direction. And it's known that when W is smaller than 3 or something, this system is ergodic. And if lambda becomes too large, this system shows many body localization. And there are several choices for this matrix M hat, but we used this. Physical meaning is obvious. At time t equals to 0 and site j, we decrease the z spin. And at time t and site I, we increase the z spin. Then I don't have much time, so I skip these two plots, which shows the f growth. And this is nearest neighbor distribution of nearest neighbor level separation. So first, this is the result for tenside, and W equals to 0.5, which is in ergodic phase. At early time, distribution is kind of close to Poisson, but then at later time, it goes close to GUE. And we can change W so that system goes into many body localization phase. Then from early time to late time, it's more or less Poisson phase. And this is a summary of numerical observations. In classical chaos, it seems that D0 brane matrix model is strongly universal. And other examples we studied, not just a matrix model, but Coulomb gas or Lorentz attractors, we studied various things. But in all cases, it looked that they are universal, but universality sets in rather late time. And in quantum chaos, SYK model is quote unquote strongly universal. In the sense, random matrix can be seen already at t equal to 0. And we only studied SYK model with integral deformation and XXZ spin chain. But it seems that other chaotic system also shows universality. And many body localization phase, which is not ergodic, is not universal. And this is my conclusion slide. And I think this result is interesting, but we don't really understand what is going on. So largest Lyapunov exponent is not enough. I'm sure about it. And the Lyapunov spectrum captures physics more precisely, of course, almost by definition. And we can see new universality. But this is just a numerical demonstration, and we don't have any, we don't know physics behind it. And the interesting thing in string theory context is black hole is probably special. It's quote unquote strongly universal. And it's very interesting observation, I think, but we don't know what is the mechanism behind it. And we don't know how we can formulate the Lyapunov spectrum in gravity side. And so far we don't know relation to the late time universality in energy spectrum. And I think from string theory point of view, it would be interesting to understand how Polygon entropy, determined from such Lyapunov exponent, is related to growth rate of entanglement entropy, for example. Or it would be interesting if we can generalize Marder-Shenka-Stanford chaos bound to Polygon entropy. Thank you very much.
Thank you. We have time for questions. Yes?
Could you clarify something that I'm sure I've misunderstood? In Kitaev's calculation, generalized later by Monosay and Sanford and others, there was one Lyapunov exponent, which came from an eigenvalue of an equation, or a zero. Well, anyway, the computation didn't seem to give a whole spectrum of exponents, but it just gave one. What is it because they took the trace of your m times m or something?
So actually, I had that conversation with many people, and here probably what is going on is so even if you take trace, in principle, you can see this sum, and if this lambda has non-trivial profile, it will give some non-trivial correction, maybe power in front of exponential growth. But nobody has seen such a thing. And the natural guess is in supergravity limit, this lambda just degenerate and become like delta function. And I think Douglas have a calculation about alpha prime correction to Lyapunov spectrum. And at least for in Fordenico, for you can have various momentum. You can see momentum dependence. In supergravity limit, there's no k dependence. You just get 2 pi t. But at the finite coupling, alpha prime due to alpha prime correction, k dependence appear. So such mechanism is hidden, and probably in SYK model, in strong coupling limit, this lambda just become like a delta function. And with the stringy correction, it has non-trivial spectrum. And our calculation is not a strong coupling limit. I didn't say, but I just took average with respect to all eigenvalues with equal weight. So it corresponds to t cos infinity.
Your suggestion, if I understand, is that in the SYK limit, this spectrum you're describing collapses?
Yes, but if you go strong but finite coupling, maybe you still see this universality, I think.
Okay.
But I don't have good enough numerical data.
Thank you.
Other questions? There.
So could you elaborate a bit on the statement you made about the SYK model at 0 time? You said it's strongly universal, and I would have expected that there would be an O1 part of the spectrum, O1 number of Lyapunov exponents, which are not, GOE or that are not maximally chaotic. Do you expect at large N you'll be exactly at random matrix theory, or there will be let's say half the exponents will be different?
So what I can say here is our n is apparently not finite, apparently not infinite, and we just took averaged all energy mode with the equal weight. So I cannot answer to that question, and it may or what you say may or may not be true, but I don't really know whether large n limit and low temperature limit commute or not. Usually not, I think. So I would bet if you take large n first and send t to small value, keeping it to be small but the order n to the 0, this universality is there. That's my bet, but I don't have data which supports it.
Okay. Other questions? Yes, there is one last question there.
So instead of the MIJ, you could also consider commutator of chi Kj correlation with, anticommutator of chi Kj with anticommutator of, say, chi K, chi L to other fermions. And then you can think that as a matrix of MIJ KL. That's just an example of different ways to capture the size of the anticommutator square. So is there a reason this is better?
I think we wanted to make an analog of this too. And honestly speaking, we tried only this, and it didn't work.
Didn't work means it doesn't grow?
Yes, so the reason is that, here, this is more or less, this inner product of this guy and the similar one. But here, this state itself can grow, but overlap with original phi can decrease. And if you go sufficiently close to classical limit, probably it can still increase, I think. But we cannot, in SYK model, we don't have classical limit. So I think that's the reason this is better. And this has apparent connection to usual OTOC this way. But this one does not have any connection to standard approach.
Okay. Thank you. Let's thank our speaker again. So our next speaker is Simeon Hellerman, and the title of his talk is Some Elementary but Surprising Properties of Quantum Field Theories.
Okay, so I'd like to start by thanking the organizers. Thank you very much, organizers, for this wonderful invitation, because this is a lovely institute and a great event. So I'm going to be talking about some work I've done over the past few years with various of my collaborators, including all Kavli IPMU alumni and a Kavli IPMU graduate student, Masataka Watanabe, really a fantastic student, already a really a fantastic researcher. And this work has been on the simplification of otherwise strongly coupled quantum systems in the limit of large quantum number. And for genericity, I'll just refer to it as J, whether it's a spin or a global charge or non-abelian global charge, whatever. So by otherwise strongly coupled, I mean outside of any simplifying limit where the theory becomes semi-classical for other reasons. Or possibly maybe in such a simplifying limit, but with the quantum number taken so large as to be greater than any other inverse coupling in the system. So greater than any other inverse loop counting parameter in the system. So the primary question is, well, why would this even be a thing? Why should you be able to get any results of any kind in such a limit? So the answer is you can, and this seems to be quite a generic situation. And in some sense, it goes very far back. by the idea of the macroscopic limit of aggregation of microscopic degrees of freedom. But recently, in the last few years, there's been a number of groups focusing on systematizing this point of view and applying it more broadly. So one can go back as far as Democritus and the atomic hypothesis, the correspondence principle due to Niels Bohr, large spin in the hadron spectrum, Regge and others in the 70s, the so-called macroscopic limit proposed by Deutsch and Schrednicki, and recently I should have said investigated systematically in CFT by Hong Liu and many collaborators at MIT. And then closer to the present, there were examples such as n equals 4 super-Yang-Mills at large R charge, familiar to many people in the audience here. Large spin expansion in general conformal field theories from light cone bootstrap, large spin expansion in hadrons. And then even more recently, when this idea, I think, is sort of come into focus as a general principle, large charge expansion in generic systems with abelian global symmetries, by myself and some collaborators at IPMU, and then many other groups in Europe and elsewhere. It was generalized to non-abelian symmetries, taking spin and charge large together. The case of topological charge has been investigated. Effective field theory analysis of large charge as overlapping with a bootstrap mode of explanation by these three authors in 2017, a very interesting work. And much more recently, the large charge limit in gravity. And so, and then also, in this interesting idea of taking large R charge in supersymmetric conformal field theories with vacuum manifolds, in which one reproduces moduli space, vacuum moduli space physics. And in some sense, large R charge gives a kind of systematic map between OPE data, such as operator dimensions and OPE coefficients on the one hand, and effective field theory of the moduli type of data. And so I'll discuss some examples of those at the end. So what are the goals of the large quantum number expansion? So we're hoping to answer the same kind of questions as are being addressed by the conformal bootstrap. So we'd like to learn to systematically and efficiently analyze quantum field theories. In practice, usually conformal field theories are easiest, with no exact solution in terms of explicit functions, because in general, quantum field theories can have chaos, as we've heard about today and earlier. So one target would be high numerical precision for known CFT, and I'll talk about some accomplishments of that kind. So yesterday, David nicely reviewed some amazing accomplishments of the bootstrap, but I would like to address Daniel's question in the Q&A after that talk. What do we hope to learn? And I would say what we'd hope to learn is, what does theory space look like broadly? And I think for many modern theoretical physicists, this, rather than analysis of particular models, is really the key type of question. And as we know, and as we heard from Laura Anderson, this is really consequential for field mathematics and cosmology and quantum gravity, field theory, the landscape. Now, most theories are not integrable. We need to know how to attack them in general circumstances. For simple systems with small numbers of degrees of freedom, direct bootstrap methods are remarkably efficient in the sense that their power law and the number of operators included and converge quickly. But on the other hand, since the number of operators grows exponentially with dimension or central charge or other limits, direct numerical attack is still intractable in general and extreme limits. And then, other than the case of large spin in a single plane, we so far do not have a handle on how to attack extreme sorts of limits directly with analytically with bootstrap. But fortunately, it seems that extreme limits of CFT in theory space or amplitude space appear to have to simplify in all circumstances that I know of, simplify in some sense. So for quantum numbers other than spin, as I say, we don't really have any analytic bootstrap methods. And the same, so even for spin in two planes, so two angular momenta, independent angular momenta in d greater than or equal to 4, we don't even know how to attack that limit with bootstrap, as far as I know. Actually, a bootstrap person is welcome to correct me, but that's as far as I know at present. And so certainly the same is true for internal global symmetries of various kinds. So then again, as David mentioned, in many such cases where such limits are accessible, to some new kinds, some newly discovered kinds of effective field theories in regions where bootstrap methods slow down. And as we'll see, there in one example where they overlap, there's excellent agreement. But so where does that leave us? Should we think of this as a duality between effective field theory and bootstraps? How should we think about this? So one modest goal would be to just translate EFT behavior into bootstrap terms, say what it means for CFT data, and see what we learn from that. Most grandiosely, we'd like to derive effective field theory from the bootstrap equations, and then solve everything. But some intermediate goal would be to use some subset of EFT inputs and maybe get some subset of CFT outputs. So the grandiose goal appears to be out of reach for me, at least, and I don't know about other people. The intermediate goal, as I say, there's been very interesting recent progress reproducing some aspects of EFT at large charge with Bootstrap. And I will talk mostly about this most modest goal. So I'm going to start with the simple example of the Wilson-Fisher conformal O2 model in 3 dimensions. So the canonical question would be, what is the dimension of the lowest operator, curly O, at large charge J? So if we translate that via radial quantization, we'd say that the energy of the lowest state of charge J on a unit sphere, what is that energy? It's the same question, transcribed into radial quantization. And so one can do a renormalization group analysis. This is a sufficiently simple quantum field theory. And one finds that the ground state is homogeneous. The ground state at large charge is homogeneous because it just doesn't have enough degrees of freedom to spontaneously break any spatial symmetries. And the radial, the magnitude of the scalar field gets integrated out, and one is left behind an effective conformal effective field theory for the phase variable of the complex scalar field. And it is an amazingly simple effective Lagrangian. It is literally the second simplest effective Lagrangian you can possibly write down. The simplest effective Lagrangian is grad chi squared. The second simplest effective Lagrangian is grad chi cubed, and that's what the effective Lagrangian actually is for this for the large charge effective theory of the conformal O2 model. Now, that coefficient b is meaningful. You can't absorb it into a field redefinition because chi is taken to have periodicity 2 pi, and we don't know how to calculate it ab initio. One could calculate it from try to calculate it various methods, and we'll see. We'll pin down pretty well what it is. But at the moment, we just leave it parameterized and see what the structure of this effective field theory tells us about the behavior of anomalous dimensions in the O2 model at large charge. So immediately, just the classical analysis of this effective field theory tells us that the lowest dimension, lowest operator dimension of charge J goes as some coefficient, which can be written in terms of b, times charge to the 3/2 power. Now, to us, that was already a surprise, and it shouldn't have been. There's just a simple dimensional analysis that tells you that has to be the case. But for some reason, we, and I think many other people actually, were expecting it to go as charge to the 1st power plus some small corrections. But it really doesn't. It's charge to the 3/2. And the leading order effective field theory predicts more than that, more than just the leading power law, because quantum loop effects in the effective field theory are suppressed at large charge. That's important. So the effective field theory can be quantized as just a weakly coupled effective action with effective loop counting parameter charged to the -3/2, even though the underlying theory doesn't have any small coupling constant. You know, we're not in the 4 minus epsilon expansion, we're not in the large n expansion, it's just the O2 model in 3 dimensions, no small coupling, but if you ask an extreme question, you get an extremely semi-classical answer. Okay. So, for instance, we can compute the entire spectrum of low-lying excited primaries. So the dimensions, spins, and degeneracies of the excited primaries are those of a Fock space of oscillators of spin L with L greater than or equal to 2. So oscillators of spin 2 or more. So the propagation speed of the chi field is 1/√2 times the speed of light. That's fixed by the form of the effective action and dictated by conformal invariance. And so the frequencies of the oscillators are 1/√2 times root L times L plus 1. Now, the L equals 1 oscillator is also present, but it doesn't give you primaries. Exciting it only gives you descendants. So the conformal symmetry is spontaneously broken, it's non-linearly realized, and the leading order condition for a state to be primary is just that there be no spin 1 oscillators excited. And of course, that gets higher order corrections, but in terms of state counting in the leading order spectrum, primary just means no spin 1 oscillators excited. So for instance, the first excited primary of charge J always has spin 2 and dimension delta sub J plus √3. So many predictions of that kind. Okay. So one can also compute subleading terms in the anomalous dimensions. So these depend on higher derivative terms in the effective action with powers of grad chi in the denominator. But these counterterms have a natural hierarchical organization in the charge, because the only thing appearing dressing denominators is this grad chi, absolute value of grad chi. There are no higher derivative dressings in the denominator. So the result is that at any given order in derivatives, there are only a finite number of unknown terms contributing. So one can compute any order with any given order with only a finite, knowing only a finite number of terms, and they're of course far more observables than effective terms. So the theory is very predictive. As far as subleading terms go, there's only one subleading term scaling with a non-negative power of j. It scales as j to the 1/2, and it's this with some other unknown coefficient. But in particular, there are no terms in the EFT that are of order j to the 0. So there are some negative powers, but nothing, no local terms scaling as j to the 0. So the result is that the j to the 0 term in the expansion of the dimension is universal, calculable, independent of the unknown coefficients in the action. Right. So in particular, the formula for delta sub j is some unknown number times j to the 3/2 plus some unknown number times j to the 1/2 minus 0.0937256 and so forth, and then terms that are subleading in j. So this universal term and other universal large J relations in the O2 model don't have any fudge factors. There are no adjustable parameters. The predictions are universal and absolute. Similar predictions have been made for the OPE coefficients. Now, I don't know, you might think there's something weird or inconsistent about a Lagrangian like grad chi cubed. I think the first time I gave this talk, the smart people in the audience thought I was just kidding around. But no, I'm really not kidding. That is the leading order effective Lagrangian. It looks weird, but isn't this Lagrangian singular? Well, no, because you never expand it around the point where it's singular. You never expand it around the vacuum. It's only meant to be expanded around a state where chi has a large time-like gradient. And so when you expand into Bevan fluctuations, each fluctuation carries a suppression that goes as 1/√j. And by the way, this type of effective action was actually the beginning of string theory. The Nambu-Goto action is of this kind. It's singular when expanded around a point-like string when thought of as an effective field theory. Right, so you could ask, isn't this EFT, isn't it UV divergent? But no, so the way to quantize it is there's a large hierarchy between the infrared scale, the size of the sphere, and the ultraviolet scale, which is set by the square root of the density. And so you put the Wilsonian cutoff in between those two, and then ultraviolet divergences are perturbative, and you subtract them order by order to maintain conformal invariance. And you can ask, well, don't the counter terms ruin everything? But no, the counter terms correspond one-to-one with higher derivative local effective terms, and we've already classified those. So we already those ambiguities are already included. So then people, insisted that we must be saying that every theory with a conserved global charge has the same asymptotic expansion, and then they tell us about some counterexample and tell us, aren't we a crackpot because of that counterexample? But no, I mean, we're not making any claim about every single CFT with a global symmetry. For instance, free fermions, free bosons, many other examples don't have this large J behavior, but more generally, a CFT can be organized into large charge universality classes. So free complex fermions, free complex scalars are different, but there are many. But the large J universality class of the O2 model does contain many other CFT, like the CPN models at large topological charge. I'll mention about that. The superconformal fixed point with a cubic superpotential for a single chiral superfield, probably lots of others as well. And then there are many other interesting large J universality classes that I think would be interesting to investigate. Some of them are already being investigated, the higher ON models, the higher Grassmannian sigma models. Chern-Simons matter theories have not yet really been investigated at this limit, but that's obviously an important direction for investigation. So superconformal theories with moduli spaces, vacuum manifolds, are obviously very interesting and inviting target for analysis. We can consider, for instance, the X branch of the XYZ model. Now, to some extent, it's boring if you just ask about the operator dimensions, because the lowest operator dimension with R charge J on the X branch has dimension J. Okay, that's because it's BPS and it can't get any corrections. That's boring. Then you can ask about the next lowest operator with R charge J, and it turns out that's also boring. This thing is what's called a scalar semi-short, and its dimension is also protected. It's exactly J plus 1. Okay, but we'd really like to do something that's not boring with this theory, so we can ask about the third lowest. We can ask about the third lowest. We can also ask about how to see directly this protection in large J perturbation theory. So we can write an effective theory, which just consists of this X field to the 3/4. The effective theory is free at leading order, but there are higher derivative terms. Again, there's a classical solution where the Vev scales as the square root of J. And one can directly compute the operator dimensions in large J perturbation theory in this effective field theory, and indeed one finds up to and including 3 loops for the chiral primary. There are no corrections. Up to and including 2 loops for the semi-short. There are no corrections. And then the third lowest, which is in a long multiplet, gets a correction proportional to 192 pi squared J to the minus 3. Where kappa is the coefficient of the leading interaction term. So fortunately, the leading interaction term was supersymmetrized recently, so we knew how to include it, thanks to Kuzenko's work. And we know by superluminality constraint that kappa is positive. Okay. So we can make many interesting predictions. And then one can also make this sort of predictions for things like OPE coefficients or 2-point functions of operators in the Coulomb branch chiral ring in extended superconformal theories in 4 dimensions. So there are many interesting theories, theories with simple Coulomb branches, one-dimensional Coulomb branches, and that's what we looked at. So some of them are Lagrangian, some are not Lagrangian, but we can treat them uniformly. So for a rank 1 superconformal theory, the Coulomb branch is generated by, it's just freely generated in all known examples, powers of some operator of dimension delta. And at large charge, the scalar is forced out onto the Coulomb branch. Right? So we can write an effective action in terms of a canonical scalar field. And the lowest state in radial quantization lives far away from the origin, and one can calculate correlation functions. For instance, the 2-point functions of powers of the generator in perturbation theory. And so it turns out that in this case, for rank 1 Coulomb branches, there's only one interaction term that can contribute to supersymmetrically protected quantities, because there are no higher derivative F terms that can even be written down due to the superviolent variance of the theory. And the leading interaction term has a coefficient fixed by an anomaly. So we'll call this anomaly coefficient alpha. It's the anomaly mismatch between the CFT and the effective field theory. So this term, this higher derivative term, was first written by Dine and Seiberg in 1997. And one can go through various manipulations to calculate these 2-point functions by standard manipulations in effective field theory. And there are combinations of these 2-point functions which are normalization independent and scheme independent, and can be evaluated straightforwardly in Feynman diagrams. So these are some of the vertices of this effective field theory, where the blue dots come from the anomaly term, and the lines are the free propagators. So we used various tricks, clever UV completions of the effective field theory, and recursion relations to compute this these 2-point functions, and there's supposed to be a gamma function inside the log. Sorry about that. But yes, so we find a universal formula for the log of the 2-point function of the generator raised to the nth power, up to exponentially small corrections. And so now I'll just talk about, in the remaining minute, confirmations of the large J expansion. So these, in the O2 model, these large charge expansions seem to be out of reach of current bootstrap methods. But there are Monte Carlo methods that can reach up to J equals 15 in recent work by this group. Right. So this curve is the theory curve fit with the unknown coefficients fit to data. Here they are, numerical values of C sub 3 halves, C sub 1 half. And you can see the fit is extraordinarily good down to J equals 2. And with those parameters fit, the agreement with Bootstrap on where they overlap is also, I think, extremely good. Right, so, and then this CPN model realization of this universality class was also worked out this year by De La Fuente. And in particular, the universal term was calculated in the large N expansion of the CPN model. And it matches the universality class to several significant digits. And so then we could also match our predictions for rank 1 superconform n equals 2 superconformal theories to localization calculations. So for free vector multiplets n equals 4, they match exactly with no corrections. For n equals 2, one can compare with localization calculations. Okay, so the line is theory with n taken up to 38 at various values of tau in supersymmetric QCD with gauge group SU2. And the agreement was so good, we can make an ansatz for the leading error associated with the breakdown of effective field theory. So you would expect the leading correction to come from virtual propagation of a massive BPS particle over the infrared scale. So you would expect something like an exponential of a constant times root j over im tau. And one can compare that ansatz with the disagreement with data, and this is what we find. So we find that the leading exponentially small correction to the large J expansion fits extraordinarily well to this ansatz in terms of virtual Dion propagation. So in conclusion, large J gives an analytically controlled way of analyzing strongly coupled conformal field theories. Agreements with other methods are very good at this point. These results have greatly improved our understanding of strongly coupled CFT and theory space overall. Thank you.
Thank you. Questions? Eva?
So, thanks for the really interesting talk. I had a question. So, is this large charge limit, is that tantamount to a finite density field theory setup? And if so, my question is, can you get a handle on transport? And does your interesting non-analytic effective theory lead to interesting transport results?
Yeah, I mean, adding entropy and temperature is a whole other ball of wax. But I think even more generally, it doesn't really correspond one-to-one with what we usually think of as finite density phases. So I didn't talk about these other cases, but in the higher ON models, generically, the ground state is inhomogeneous on the infrared scale. So it's not like a striped phase, but in general, the charge distribution takes the shape of the box it's in. So it doesn't really correspond to an extensive.
Sorry, what does that mean? It takes the shape of it's distributed how inside?
Some solution which has a characteristic variation of the infrared scale. So in papers this year with my students, we worked out some examples. For like the O4 model, this happens even. The O4 model at generic large charges has a ground state inhomogeneous on the infrared scale. Right. It's not what you would call a finite density phase in the usual sense.
Okay.
This is a comment. I mean, one can explain this O2, the dimension, which is proportional to J to the 3/2.
Yes.
That one may be explained by assuming, gravity dual, existence of gravity dual, and then studying corresponding RN, ADS, black hole in the extremal limit.
It's not in the holographic regime, but people have.
That I understand.
People have recently tried that. Yeah. Yeah.
Okay. Any other question? So, don't see any. So let's thank our speaker again. Last speaker of this session is Greg Moore, Global Anomalies in Six-Dimensional Supergravity.
So, is that up? Keep an eye on the computer. Well, I can't see it. I can only see the back. Okay. Now if I go over here, I can keep an eye on the computer. All right. Well, thank you to the organizers for inviting me to speak. There are many of you out there with great things to say who have not had the opportunity to speak. So I'm very keenly aware of the honor. So what I am going to speak about is global anomalies in six-dimensional supergravity. And I'll talk about a paper I wrote with Daniel Park and Samuel Monnier last fall, and work in progress with Samuel Monnier. So here's the outline, and you'll see it again. So the motivation, it's going to be hard to manipulate this. Okay, the motivation for this talk is the relation of apparently consistent low-energy supergravity theories to string theory. And here is a Venn diagram from Waddy Taylor's Tassi lectures. And the red are the apparently consistent low-energy supergravity theories, and the green are the consistent string compactifications. And we'd like to find new consistency conditions to shrink the red and new constructions to grow the green. And the interesting question is whether the twain shall meet. And the state of the art in this science, at least as of last summer, is summarized in some nice Tassi lecture notes by Daniel Brennan, my very good student, Federico Carta, and Kumran Vafa. So something happens with the PowerPoint, and my animations that I spent hours and hours on are not working. But we'll deal with it. You did do the final, right? It's a PDF file. All that work for nothing. Okay, so right. So the summary of the results is that well, we're going to focus on six-dimensional supergravity, and people have studied that before, and we're going to do a more systematic study of global anomalies than has been done hitherto. So the first result is a necessary condition that unifies and extends all previous conditions. And the second result is at least a framework for a complete, necessary, and sufficient condition for global anomaly cancellation. I'll define a certain seven-dimensional topological field theory. The statement of global anomaly cancellation is that Z topological is trivial, but I hasten to add that the effective computation of Z topological remains open. So much as I wish I could tell you we've completely nailed this problem, there's still something to do, effective computation of something we define. And finally, we won't have time for it, but we did a check in F-theory. The novelty there is that it's important to know the global form of the gauge group, not just its Lie algebra, at least the identity component of the gauge group. So let's have a few brief words on the six-dimensional supergravity and the Green-Schwarz mechanism. So what you might call the pre-data of six-dimensional supergravity is just the field content. A 1-0 supergravity multiplet, vector multiplets, hypermultiplets, and tensor multiplets. So for the vector multiplet, what we choose is a compact Lie group. Just a compact Lie group, possibly disconnected. For the hypermultiplets, a quaternionic representation of the Lie group. And for the tensor multiplets, we choose a Lorentzian signature integral lattice. That's going to be the lattice of string charges. So we could call that the pre-data. Now, then we can write multiplets, Lagrangians, equations of motion. Here's a table of the field multiplets, and you notice the pluses and minuses on the fermions and on the B fields. The fermions are chiral, symplectic Majorana-Weyl, and the two-form field strengths are either self-dual plus or anti-self-dual minus. Now, that means that they're gauged in gravitational anomalies, and from this pre-data, we compute, following textbook procedures, an anomaly 8 form, which is a complicated expression in terms of the Chern-Weil representatives of characteristic classes. So in the Green-Schwarz mechanism, what we have to do is we have to factorize this I8 as a half y squared. Y is a 4 form. 4 plus 4 is 8. It's also valued in a vector space lambda tensor R. Now remember, lambda is a lattice, so it has a quadratic form. So the vector space has a Lorentzian signature quadratic form. So when I write y squared, it's understood that I'm using that quadratic form to contract the two factors. So we interpret y as a background magnetic current for the tensor multiplets. We write dH equals y. That implies that the B field transforms under gauge and gravitational transformations. And we add a counter term to the supergravity action, and the perturbative anomalies cancel. And at this point, some people, there'll always be some people, who will say, so what's the big deal? You wouldn't want to be one of those people, right? Yeah, some people can't appreciate that there are subtleties. So let's look into this in a little more detail. Let's first try and factorize I8 as the square of y. And to do that, it's useful to write the Lie algebra of the gauge group in terms of a sum over the simple sum ends. G sub I is a simple Lie algebra, and choose a basis for the abelian part. And then we can write out the general form for y like this. So P1, C2i, these are Chernvey representatives of characteristic classes. The metric goes into P1. The ith gauge field goes into C2i. The abelian factors are over here. Now, these multiply vectors, A, B sub I, B sub ij. These are vectors in the vector space spanned by lambda. These are by definition the anomaly coefficients. Now, the very existence of such a factorization puts constraints on this pre-data, and those have been well explored. See, for example, Waddy-Taylor's lectures. So, for example, the cancellation of trace r to the fourth is 0, a has to square to 9 minus t, and then there are a bunch of other very complicated constraints involving various Casimirs and dot products of a and b. Now, if you have a factorization, there can be multiple factorizations of the same I8. So the full data for 6-dimensional supergravity is gr lambda and choice of a and b. So for any gr lambda a and b, adding the Green-Schwarz term cancels all perturbative anomalies, and all is sweetness and light, except there are solutions of the factorization conditions which cannot be realized in F-theory. We haven't taken account of global anomalies, and a fuss budget might wonder if the Green-Schwarz counterterm even makes mathematical sense. So that brings me to the quantization of the anomaly coefficients. So, as I said before, global anomalies have been considered before. We've just been a little more systematic. And to state the best result, we note that we can assemble the bi and the bij into a single quantity. It's a quadratic form on the Lie algebra valued in this vector space lambda tensor R. After all, these Chern classes are defined by using a quadratic form on the Lie algebra, and so we're just multiplying them by these vectors. So the vector space Q of such quadratic forms is something that arises in topology. It has a name, H4 of BG1 with coefficients in this vector space lambda tensor R. G1 here is the is the connected component of the identity element in the Lie group. Now, inside that vector space Q, there is a lattice, H4 of BG1 with coefficients and lambda, and our result says that B has to be a vector in that lattice which is divisible by 2. That abelian group has no torsion, so that makes sense. Now, a derivation of this, we gave several derivations in our paper, but the simplest one is just to say that a consistent supergravity can be put on an arbitrary spin sixfold with arbitrary gauge bundle, and then the cancellation of background string charge in a compact Euclidean spacetime requires that this background charge, here I've integrated over a closed force cycle, has to be canceled by string charges, and lambda is the lattice of string charges. And so from this condition, with some processing, you get into this statement that I said before, that B is in this lattice H4 of BG1 lambda. Now, that's a necessary condition. It subsumes all the previously written conditions in the literature and extends it, but it's not a sufficient condition. So to get a sufficient condition, we're going to have to revisit the Green-Schwarz mechanism. So the goal now is to understand that mechanism in more precise mathematical terms. The benefit will be that we'll recover the constraints that I just mentioned, and some that I haven't mentioned yet, that A is a vector in the lattice lambda, and that lattice lambda has to actually be unimodular, self-dual. And the benefit here is also that we'll derive a new constraint, namely that this anomaly coefficient A is what's called a characteristic vector of the lattice lambda. So for those who don't know, if you have an integral lattice lambda, you can consider v dot v modulo 2. And if you think about it for a moment, v squared modulo 2 is actually a linear function of v. If it's a linear function of v, it should be written as v dot a mod 2 for some vector a. Such a vector A is called a characteristic vector. Why is this interesting? Well, it was observed experimentally in all F-theory compactifications that the vector A is a characteristic vector, but no low-energy effective explanation of that was given or had been given until today when I'm giving you. So now we're going to revisit the Green-Schwarz mechanism. You might ask yourself, well, what's wrong with the textbook Green-Schwarz mechanism? Well, actually, a lot of things are wrong. What does B even mean when M6 has non-trivial topology and H is not closed? How are the periods of dB quantized? And does the Green-Schwarz term even make sense? So your impulse when you see this should be, well, let's extend this to 7 dimensions, U7, because dB is, after all, much better defined than B, but this better be independent of the extension to U7. But it isn't. Even if you take the difference of two B fields, well, the difference of two field strengths, H1 and H2, will be a closed form. It's reasonable to quantize it so it has lambda periods, but then there's this pesky factor of 1/2. I've been careful about my normalizations, and even the difference of Green-Schwarz counterterms is not well defined. So we have to go deeper. Now that brings me, and the way we go deeper is we think about this geometrically. So we'll think about the geometrical formulation of anomaly cancellation. So in this context, what that means is that you look at the space of all fields in 6-dimensional supergravity as fibered over the space of non-anomalous fields, the metric, the vector multiplet gauge connections, the scalar fields. And you organize your partition function as an integral first over the anomalous fields, Fermi and B, and then over the non-anomalous fields. Now, the integral over the anomalous fields involves determinants of Dirac operators, and so a priori it's a section of a line bundle. And even in the most formal sense, you cannot integrate a section of a line bundle against a measure. You can integrate a function against a measure, but not a section of a line bundle. What you have to do is what the mathematicians say is geometrically trivialize. Identify a section of your line bundle with an actual function. Okay, so that was the point of view on anomalies back in the early 80s. This subject was very popular in Boston, in Oxford, but it has a modern formulation in terms of something called invertible field theory. Now, when I say invertible field theory, the term field theory, which probably means something different to most of you from what I mean right now. So field theory, in invertible field theory, is in the sense of the mathematicians like Atiyah and Graham Siegel, Dan Fried, Mike Hopkins. It means a rule that for a d-dimensional field theory, to a closed D-manifold, you associate a number. That's the partition function. To a closed D-1 manifold, you associate the space of states, the Hilbert space of states, and so on, satisfying gluing rules. Well, an invertible field theory simply means that the partition function is an invertible number, and the Hilbert spaces are one-dimensional, and they satisfy gluing rules. Now, Dan Fried, in a very nice paper, explained how you can take the old geometrical interpretation of anomalies, previous slide, and interpret it for anomalies in a d-dimensional field theory in terms of a d+1 dimensional invertible field theory. That's the point of view we're going to take here. So we'll interpret the anomaly as a 7-dimensional invertible field theory constructed from this data and the non-anomalous fields. So the data for this invertible anomaly field theory is a metric, a spin structure, and an actual connection on the G bundle P. So it's not a topological quantum field theory. Now, that on a 6-manifold, we get a 1-dimensional space of states. If we now vary the metric and the connection, we get a line bundle over the space of metrics and connections. And psi anomaly is evaluated on a 6-manifold as a section of that line bundle. Here we go. And so that's the relation to the old geometrical interpretation of anomalies. So how does anomaly cancellation look in this language? Well, it's 2 steps. You first construct a counter term, 7-dimensional invertible field theory, transforming in the opposite way from the anomaly one. And then, just using the data of the 6-dimensional fields, you give a local construction of a section of that line bundle. All right, that's non-trivial since we're doing that in a 7-dimensional field theory. Then you can insert that in the path integral over the anomalous fields, and you get a function on B mod G. So let's explore the anomaly field theory for 6-dimensional supergravity. It's expressed in terms of something called Dye-Freed theory. So what's Dye-Freed theory? So if D is a Dirac operator in odd dimensions, you could take basically the eta invariant, more precisely this psi invariant, and then e to the 2 pi I psi defines an invertible field theory. So on an odd manifold without boundary, you get a number, that's the partition function. On an odd manifold with a boundary, this is interpreted as a section of a line bundle over the space of boundary data, and suitable Lewing rules hold. The anomaly field theory for 7-dimensional supergravity, then, is a sum of Dye-Freed theories. So we have a sum of eta invariants for the various chiral Fermi fields, and also you can show eta invariants for Dirac operators associated to the self-dual and anti-self-dual fields. On 7 manifolds with boundary, then, this set of eta invariants defines a section of the anomaly line bundle. Now, in general, eta invariants are totally off limits. They're impossible to calculate in terms of anything simpler. However, if the matter content is such that I8 is a half y squared, and if U7 and its principal G bundle is Borden to 0 means extends to an 8 manifold, then there's a very simple expression for the partition function in 7 dimensions. It's the integral over that 8 manifold of a half y squared up to an 8th root of unity. That does, of course, raise the question, when can you extend your principal G bundle in 7 dimensions to an 8 manifold? And that brings us to spin-Bordism theory. Now, mercifully, the 7-dimensional spin-Bordism group is 0. And what that means is if you have a closed 7-dimensional spin manifold, yes, you can find an 8-dimensional spin manifold of which it is the boundary. However, this spin-Bordism group in general is not 0. And what that means, if you have a G bundle over U7, there can be obstructions to extending it to a G bundle over a bounding 8 manifold. Fortunately, omega 7 spin of BG is 0 for many groups of interest. UN, SUN, SPN, E8, products thereof. However, there do exist compact Lie groups for which this spin-Bordism group is non-zero. For example, just cyclic groups will do. All right. Now, let's assume that we're in a situation where we can extend to 8 dimensions, and I'll come back to the case when we can't later. So when the 7-dimensional data does extend, we have this very simple formula, and the importance of this formula is it gives us a clue to constructing the counterterm anomaly, the counterterm invertible field theory. So Z anomaly looks like this. Well, what I've done here is I've uncompleted the square. I've written x as y minus a half lambda prime. Lambda prime is a tensor lambda. Lambda is a half p1. And so I've written this y squared instead in this form. And you'll see why on the next slide. Thanks to our quantization condition on B, this x is a closed form with periods in lambda. Okay, now this expression, let me call your attention to the fact that this expression is independent of extension only if A is a characteristic vector. Remember, that's something we want to explain. We want to explain why is A a characteristic vector. Now, I'm excited about this formula because this is the partition function of a 7-dimensional topological field theory known as Wu-Chern-Simons theory. Wu-Chern-Simons theory is just a natural generalization of spin-Chern-Simons theory in 3 dimensions. So in our case, it's been developed in great detail by Samuel Monnier. In our case, we're looking at a 7-dimensional Wu-Chern-Simons theory of a 3-form gauge potential with field strength x quantized in lambda. Spin-Chern-Simons theory depends on a choice of spin structure. In just the same way, Wu-Chern-Simons theory depends on something called a Wu structure, which is a trivialization, I'll call it omega, of the fourth Wu class, and if it makes you feel better, this is how it is written in terms of Stiefel-Whitney classes. Actually, in our case, it is just the fourth Stiefel-Whitney class. So we actually have to choose a trivialization in 6 and 7 dimensions, and our Wu-Chern-Simons theory depends on it, just the way a spin-Chern-Simons theory depends on spin structure. But nevertheless, our partition function of a Wu-Chern-Simons theory looks very much like the thing we're trying to cancel. Again, lambda prime has to be A tensor lambda, and A has to be a characteristic vector of lambda. And in order for this to be an invertible field theory, lambda has to be a unimodular lattice. So now what we want to do is we want to define our counter term, invertible field theory, in terms of Wu-Chern-Simons theory, but there are two problems here. First, we want to apply it to Y. Y is the thing we construct out of the metric and gauge connection, but it has the wrong periods. It's shifted by this. And the second problem, as I've been stressing, is that Wu-Chern-Simons theory depends on a choice of Wu structure, and I'm sure you will all agree with me that we do not want to add a choice of Wu structure to the data defining six-dimensional supergravity. So the solution to this is that given a Wu structure, we can shift Y in a Wu structure dependent way so that if we evaluate Z, Wu-Chern-Simons, on that X, then it's independent of Wu structure. That's good, so it drops out. Also, it transforms properly under B-field diffeomorphism and vector multiplet gauge transformations. So now we put these two things together, and we get a 7-dimensional topological, don't show all my tricks, and we get, okay. All right. Who's on first? Okay. All right, so yeah, we put these two invertible field theories together, and what we get is this is a definition of a 7-dimensional topological field theory that is defined on Bordism classes of G bundles on spin manifolds. So its partition function is a homomorphism from omega 7 spin of BG to U1. If that homomorphism is trivial, our topological, Z topological is trivial, and we're in good shape. We can proceed with anomaly cancellation, so let's proceed. Time is running out. So let's suppose the 7D TFT is trivializable. We still need to construct a section which is local in the 6-dimensional fields. That will be our Green-Schwarz counterterm. We insert it in the path integral over the anomalous fields. We get a function on B mod G. We're all happy. Okay, so now this is where we actually have to start getting technical to make actual sense of what I've been saying, and also to construct the counterterm, the Green-Schwarz counterterm. So, basically, it's a matter of understanding differential cohomology, which at some level is replacing H by H check. And I'm reminded of a great story in Peter Freund's delightful book, A Passion for Discovery, about his being a postdoc with Stuckelberg and the great importance of adding checks and hats and dashes to your notation. Here it's also very important because differential cohomology is much bigger than ordinary cohomology. It's a precise formalism for working with p-form fields in general spacetimes, and by the way, p-form global symmetries. You see, if you have a p-form, there are 3 independent pieces of gauge invariant information. There are the Wilson lines, there's the field strengths, and then there's the topological class. And these are all united into one infinite dimensional abelian group that nicely accounts for how these things fit together. And there is an exposition for physicists in a paper I wrote with Dan Fried and Graham Siegel. So just to show you there is a formula using this formalism, this is our formula for the Green-Schwarz counterterm. What to remark about it? It's a section of the right bundle. Several of the moving parts involve this Wu structure, but the whole thing has no dependence on Wu structure. It's locally constructed in 6 dimensions, and it makes sense in topologically non-trivial cases. And of course, it locally reduces to the expected answer. So in conclusion, all the anomalies cancel for GR lambda A and B such that I8 factorizes. A is a vector in just in a unimodular lattice. It's a characteristic vector, and A squared is 9 minus T. And half B is in this lattice, provided this spin-Bordism group, which you can't see, the green on green, the spin-Bordism group is 0. Well, I don't want you to see it because, you see, all is sweetness and light, except that we'd like to relax that last condition, right? But then this Z topological could be a non-trivial topological field theory. If it is, we're dead. Then the theory is anomalous. So that's where we are. So we need to understand better how to calculate this 7-dimensional topological field theory. We've now done some calculations to show that if the spin-Bordism group is non-zero, there will be new conditions. Examples now exist. And so finding these new conditions in complete generality looks like a very challenging problem. Let's see, that's 26, 27. That means I have 4 minutes? I have minus 1 minute? Okay, so now you want to check this in F theory, and you want to make sure that the Venn diagram doesn't look like that there aren't F theory compactifications that are anomalous, and in a word, it's okay. So that concludes the scientific part of my talk. Sorry for the minus 1 minute, but I do want to take just 2 minutes to say something else. I'd like to say something about Joe. So I don't need to tell this audience that Joe was a great physicist, but he was also a good friend. And I met him in the early 80s. And I'm grateful to Joe for many, many things. And I'll just tell you one. You know, it's very rare that you go to a seminar which is so good that it completely changes your career path and your research. And Joe gave, for me, in my case, Joe gave such a seminar, again, at Harvard in the mid-'80s. It was so beautiful, so clear, everything right on point, and so full of enthusiasm that it set me on a good path and a good collaboration with him. So I'm very grateful to Joe for that, and as I said, for many other things. Joe, as you all know, was a great scientist, but also a great human being. He was good-natured, full of good humor, enthusiasm, and most of all, rock-solid integrity. And he's somebody I think we should all try to emulate. So finally, I'd like to offer a huge thanks to the organizers for a superb conference. Thank you very much.
Thank you very much. Questions? Yes?
Non-gravitational. Well, sure, there can be global anomalies. A lot of this, some of you will have noticed that a lot of this has the same flavor as discussions of non-trivial topological phases. And that's more about investigating the global anomalies in various states, which need not be gravitational indeed. So I haven't thought hard about that. I've been focusing on the supergravity case, but there's definitely overlap with those methods, topological phases, and therefore non-gravitational theories. Yes, John?
John?
Is there an analogous analysis in 10 dimensions?
Yeah, 10 dimensions is really different. The answer, by the way, is yes. Dan Fried wrote a paper in around 2000 or 2001 entitled something like Dirac quantization. And at the end of that paper, he gives a very careful analysis, a mathematical analysis of 10-dimensional Green-Schwarz cancellation. He doesn't phrase it the way I've said it in terms of invertible field theory, since that concept hadn't really been invented yet. But he does discuss that. And there's a very, very interesting issue there, which is that he models the B field using K theory. Whereas here, I made a choice when I discussed the B field in precise mathematical terms. I made a choice of generalized cohomology theory. And it is conceivable that there could be a K-theoretic formulation of the B field in which the story of which theories have global anomalies and which do not would actually change. So this is actually a case where potentially this seemingly extremely arcane issue of which generalized cohomology theory you use to quantize your P-form fields could really matter. But we don't know. So Samuel and I have, just as a working hypothesis, used ordinary differential cohomology, or a slight variation of that called E theory.
Maybe one last question. Yes?
Yeah, nice talk, Greg, about some impressive and I think exciting work. So I have a question actually about your derivation of the self-duality condition
Right.
on lambda.
Right.
So do I understand that just comes from the statement that you have this invertible field theory? And does it not depend on the presence of any gauge? If you have no gauge fields, this is still true?
Well, you always have gravity.
Sure.
So
If you just have gravity,
you always have gravity. So yeah, so this condition that lambda is self-dual is a nice result of Nadia-Seiberg and Waddy-Taylor, where they basically derived it as a global anomaly condition. Their idea was to compactify from 6 to 2 along a 4 manifold and observe that you should have proper modular transformations in 2 dimensions that forced lambda to be even. Sorry, I keep saying even, and that's really, really seriously wrong. It forces lambda to be an integral unimodular self-dual lattice, not even. Here, as you just said, it comes out in a different way by insisting that this Wu-Chern-Simons theory be an invertible field theory. So that actually brings up another point which I should stress, which is, so I derived that lambda is unimodular and that A is a characteristic vector. So those are new results. But I derived that by saying, I need this for my counter term anomaly field theory to make sense. Now, logically speaking, that doesn't completely rule out the possibility that somebody smarter than me will come along with a totally different construction of anomaly cancellation. I think it's extremely unlikely because the anomaly field theory gives me the 1/2 x plus lambda. So what else could it be? But logic, I think in strict logic, that possibility remains open.
Good. Good. Just to sort of finish that, so can you say like 2 sentences about why the fact that the field theory isn't, why you have an invertible field theory implies the unimodular? Is that this or?
Yeah, because when you calculate the space of states, you're going to meet the discriminant group.
Good. I see. So you say you just see it immediately in that field. Thanks.
Okay, well, we are behind schedule, so we should stop here. And let's thank Greg again. Thank you very much.
So I have one announcement to make. So just as the conference is ending, I'm told that weather is changing. So on Sunday, there's a possibility that typhoon might approach Okinawa. So I'm told that by secretary that if your flight is leaving on Saturday, it's most likely okay. But if you are planning to stay longer, you may want to check with the forecast. So I was told to announce that.